Okay, everybody. So now that we've had our homework discussion and whatnot, we can go ahead and just get right into the wonderful world of concentrated moments and fixed supports, because that's really our discussion point for today is dealing with concentrated moments. And a fixed support is really just a pinned reaction that has one more reaction. It's a concentrated moment reaction. So really, concentrated moments are the star of the show today. I'm going to give you a homework assignment. I do honestly believe it's easier than the one you just did. I really believe that. I don't know if you will, but I promise I do. Did everybody get the code? All right, so let's jump right in. Okay, so let's just take a step back and discuss what we've done so far. And so what I'm trying to do with this topic of support reactions is I am trying to introduce the tools of structural analysis that we're going to use throughout the semester, but I am also trying to ramp it up just a little bit each time so that when you get a problem that looks crazy, it's really not. It's just taking that problem and deconstructing it into the components that we know how to deal with on an individual basis. And so up until now, we've dealt with concentrated loads, we've dealt with distributed loads, and those distributed loads could either be uniformly distributed or linearly distributed like a triangular load. We've dealt with inclined loads, we've dealt with pin boundary conditions, we've dealt with roller supports. So we are going to add to that. Okay, and so what we're going to be talking about today are concentrated moments. Okay, now concentrated moments really come from two areas in the real world. The first area is torsion. Okay, so for example, if you have like a beam right here, and you have an element framing into it that's being twisted. So here's the beam, and right there at that one point in the beam, it's experiencing this concentrated twisting effect right at one point. So if you ever have, for example, like another example is, okay, here's a structure, here's a floor beam. Let's say this floor beam is on like a sort of a balcony type structure. So the balcony is sort of bending down. This floor beam is going to be bent, and this little spandrel is going to be twisted, so the column is going to experience a sudden twisting right where this element frames in. Does everybody kind of see that? There's a sudden little right there, okay? Another place that you see concentrated moments is a fixed support, okay? So the idea is, okay, imagine you had like a flexible ruler in your hand and you've got a solid grip on it, okay? And then you take that and you press down. Not only does your hand have to keep the ruler up and down, but if you're pressing like this, the ruler is going to want to twist. You have to take your hand and rotate it back, okay? So it's that backwards rotation, that concentrated that you've got to do. That's a concentrated moment as well. I should also mention that even if a structure does not have a concentrated moment present on it, you do still need to be able to deal with concentrated moments with structural analysis, okay? Concentrated moments are going to be a tool that we use for particular types of analyses later, specifically when we compute deformations. We're going to get into a world a little bit later this semester where we're using what's called the principle of virtual work in order to compute deformations. And so whenever you're computing deflections or rotations and whatnot, you have sort of two structural analyses you have to perform, and one of them is a virtual analysis where you take all the loads off the structure and you put a single load on the structure that's indicative of what you're trying to figure out, and that might be a concentrated moment. So you do need to be able to deal with them even if there are no concentrated moments in real life on the structure. Okay, so I want to do a quick couple problems with you on dealing with concentrated moments. Okay, so we'll start with this problem. I have an overhanging beam here. Let me bring up the notebook. And again, we haven't dealt with one like this in this class, but again, I want to reiterate that this is no different than what we have been doing this whole semester. It's just some things a little unique. We have this concentrated moment there on the structure. Now, when I draw these on the board, or in my slides, what I've done here is here's the concentrated moment. I put this little plus here to sort of indicate that the moment is right there. just so you kind of know what point I'm talking about, okay? So we have a concentrated moment on this outer span of 20 foot kips, okay? And again, I think you'll be surprised how easy these are to deal with. Okay, so again, we're going to handle this like we've handled any problem in this class, okay? So first thing we'll do is we'll identify our unknown reactions. How many unknown reactions do we have for this problem? 3. We have 2 for the pen supported A, 1 for the roller supported B. Okay, I'm gonna put this reaction there, put this reaction here. And we'll just assume they're both upward, okay? We'll put a horizontal reaction right here. We'll talk about that here in a second. We'll just assume it acts to the right. Okay? Now, we're going to look at this distributed load next. So tell me what to do with this distributed load. What should I do? I should idealize that. But tell me what to do.
Should you turn it into a point load?
Okay, and how much is that point load?
30 kips.
Okay, and where do I place it?
5 feet.
5 feet from right here?
Yes.
Okay. Okay. All right. Now, I want to make a point that even though there's a concentrated moment present on the structure, the our strategy for computing support reactions doesn't really change, okay? So what I'm going to do is, sort of this discussion here is really sort of a good way of transitioning to this. I could still sum moments at A or sum moments at B if I want. I'll sum moments at A, just kind of like, I like working from left to right. So I'll sum moments at A in order to isolate and compute the unknown reaction at B. Same as I've done before, right? No different, okay? So let's go ahead and do that. Let's sum moments at A. Now I'm going to scroll this just a little bit so it's a little bit easier for me to write on here. Okay. So let's just take this one step at a time. Do I need to consider, if I'm summing moments at A, do I need to consider AX or AY? No. Okay. Do I need to consider the 30 kips? Yes. Okay. The 30 kips generates moment. What side of the table does it go? Left or right?
Left.
Left. Okay. So 30 kips times a moment arm of 5 feet from A, okay? And again, the idea is, here's what we've got going on, okay? So, that marker's not good. So again, we've got, here's point A, here's a load, right? So there's a line of action that goes forever, and we're just trying to figure out the shortest distance. That's what we're trying to do, okay? All right, moving from left to right, I have BY. Does BY generate moment?
Yes.
Yes. Which side of the table, left or right?
Right.
Right, and that's going to be a moment arm of 25 feet. So we'll put BY times 25 feet. Okay. Now working from left to right, now we've got the star of the show for this problem, and that is the moment, okay? So I'm going to ask a silly question. Does that moment generate moment? Yes. We're going to have to consider it. Of course we are. Okay? Now, what side of the table does it belong? Left or right?
Left.
That's easy, right? Because it's literally rotating that way. Okay. Now, here's the question. What distance do I multiply by?
You don't. No.
You don't, right? What are we doing with this? We are summing moments. That's a moment. So just list it as 20 foot kips. Don't multiply it by a distance. So it's very tempting here to say, oh, it's 20 times 35 because it's 35 feet away. it already is a moment, okay? So don't multiply by distance, just tack it on. That's it. That's the only thing. That's all there is to it. Everything else is exactly the same. Did I forget anything?
Yeah, 10 kips.
10, the 10 kips. Times the moment arm of
45 feet.
45 feet. And that's it, right? So 30 times 5, that's 150. That's 450. So 150 and 450 is 600. 600 plus 20, that's 620 foot kips. Boom. No different. It's no different at all. Okay? So therefore, By is what? I might need some help on that.
24.8.
24.8. Do I have a second? I got a positive answer, which means that my assumed direction is correct. Boom. Okay. So far, so good? All right. So I'm going to go ahead and steer the ship a little bit. I'm going to go ahead and say let's sum forces in the y direction. Okay? Okay. So, and I'm being methodical here probably more than I've been maybe in the last lecture because, again, I'm trying to make a point. Do I consider AX? Why don't I consider AX here?
Because it's not in the y direction.
Because it's not a force in the y direction, it's a force in the x direction. So, do I consider AY? Yes. Do I consider the 30 kips?
Yes.
Yes. Do I consider BY?
Yes. Yes.
Do I consider the 20-foot kip moment? No. Why?
It's a moment.
It's not a force in the y direction, right? You wouldn't consider the 20-foot kip moment for the same reason you wouldn't consider AX. We are summing forces in the y direction. That is not force in the y direction, okay? So it doesn't fit, it doesn't factor in here. Again, I'm not saying that AX doesn't matter, and I'm not saying this doesn't matter. I'm saying this is what we're doing. That's not a force in the y direction. So we just don't consider it, okay? We do consider the 10 kips. Okay. So we have AY plus 24.8 kips is 30 and 10 makes 40. So AY is 40 minus this. So I think I can do that in my head. Was that 15.2? Did I get that right?
Yeah, good job.
Thank you. I like the support.
You're welcome.
Support reactions. That was a really bad joke. That was really bad. I'm gonna add 0.1 to the mistake counter just for that, 'cause that was a really bad one. Nice try. That was good. That was good. I love my job. Okay. All right. So, okay, I'm kind of, I did it this way because, let's be clear, we do still have one more equation of equilibrium, okay? And that is summing forces in the x direction, okay? Okay? And if I sum forces in the x direction, what is AX?
Zero.
It's 0. Do I account for this 20-foot tip moment when I'm subbing forces in the x direction?
No.
No, because it's not a force in the x direction, okay? And I'm really trying to harp on this because I have graded quite a few structural analysis exams in my day, and this is the type of thing that when you're taking an exam, this just finds its way here and finds its way here, and it's not there. So I'm really trying to emphasize that this is a lot easier than it sometimes appears on a celebration. So this is our answer. Okay. So let's take a step back. Did this make sense? Everybody okay with this? I like this. All right. All right. Any questions to it? Yes?
I was wondering for like visualizing it. So it's a 20-foot kip. Would that be like there's something coming out of the page, like turning it down almost?
Yes. I'm going to do my best to, okay, this is going to test my 3D art skills, so bear with me. I'm going to keep this picture here. I'm going to do my best. So let's say that we have a beam like this. Okay, so what we're looking at right here is we're looking at this beam like that. Okay, so this is this beam, the one that we just did. So there's the load here, there's the moment there, and so on and so forth. Okay, does that make sense? Okay, so I'll try and draw this in a way that makes sense. Okay, so this is about the simplest physical explanation I can give you. So let's say we've got an element that sort of frames in like that. Like right here, okay? And then imagine that you were standing right here. What would that do right there? It would twist it, you know what I mean? Like that sudden point would experience a twist, okay? Now, I want to, you're making like it's a good question and you're raising a really good point. So I want to say two things, okay? Number one, again, even if a concentrated moment inside a structure seems like a structural rarity in the real world, we do still need to be able to handle it as an analytical tool for later, okay? So just give me a little bit of faith on that one, okay? But there is a larger point that's maybe worth mentioning, and that is that more often than not as structural engineers, we try and avoid torsion. We don't like torsion. Torsion is not very amenable to the shapes that we use in civil engineering. For example, I shapes are very weak in pure torsion. They are very wobbly when it comes to being twisted, and we try and avoid that. Sometimes it happens and we can't get around it, but you know, it is what it is. But a lot of times we don't see stuff like that for that very reason. Okay. Does that make sense?
Yeah. So like a negative moment would almost be going like into the page.
Yeah, and what we are going to see here in a second is a fixed support, where that is probably the most common real world example of a concentrated moment. We're going to deal with that like in the next couple minutes. So.
Okay.
All right, did my 3D art, that's about the best I can do. Okay. All right, so let me go back here. Okay, so So the one thing that, the one place where you really are going to get concentrated moments very frequently in civil engineering contexts are with cantilevers, okay? So any time that you have an element that's sort of jutting out in space and whatnot, there's usually a concentrated moment right here at this support that the structure has to be able to withstand. Common examples of that include balcony type structures in building systems and whatnot. I mean, there's balconies and mezzanines all over the place in commercial structures. So you're going to see cantilevers quite a bit in those contexts. It might seem kind of strange to say that you would see cantilevered sections in bridges, because you would think, well, doesn't the bridge have to like connect on the other end, so we don't have, you know, like a Evel Knievel Dukes of Hazzard situation. But there are instances where certain elements of bridges are considered cantilevers. One example that I kind of like to use is a hammerhead pier, okay? So I imagine everybody has seen stuff like this before. This would be the central support on a multi-span bridge. So whenever you're designing the reinforcement inside this hammerhead pier, what you would often do is you would say, okay, here's the pier, right? Okay, we'll just look at half of it. You've got a beam right here, a beam right here, and a beam right here, and we'll treat this as sort of a fixed support and figure out how much reinforcement needs to go right here. Because, see, what's happening, okay, right here at the pier, okay, is you've got a ton of force right here and a ton of force right here and a pier in the middle. So it's almost like this pier cap right here, what's happening is it's kind of wanting to bend like this. So there's a ton of moment right here, okay? And concrete, one of the things that we'll talk about one of the things that your civil engineering materials professor will talk about is that concrete is a material that behaves very well in compression but very poorly in tension. And so what's happening here is that the top is experiencing a lot of tension possibly, okay? So what we're trying to figure out is what's that moment to figure out how to detail the rebar that goes this way to prevent the cracking that way, okay? So we'll treat it as a cantilever in that context. Does that make sense? So whenever you have a cantilevered support, it has three reactions. It has a vertical reaction, a horizontal reaction, and an unknown concentrated moment reaction. But I will say that, and again, I hope you believe me, that cantilevered beams like this are among the simplest from a reaction computation standpoint. And you'll understand what I mean when we get through this example here in a second. Okay. So let me see if I can convince you that these really are, in fact, very easy structures to deal with. Okay. So first off, I'm going to deal with the inclined load first. This is a 3 to 4 slope ratio. So I'm going to split this up into X and Y components. Okay. So first off, what is the Y component going to be? If this is let's be clear, this is a 3, 4, 5. So what's the Y component going to be? It's not a roller, this is just the load. What's that? So, well, let me put it this. Okay, I'm going to take, let's try it like this. I'm going to take 10 kips times a fraction. 10 kips times a fraction. What fraction goes right here?
4/5.
4/5. There we go. Okay. And 10 kips times over here, 10 kips times 3/5. Okay. So remember, whenever you're doing these fractions, whenever you're taking an angular load and splitting it up into X and Y components, the denominator is always going to be the hypotenuse. Okay. The numerator is going to be, either the vertical or horizontal index. Okay. But you're always, the idea is that If you have an angular component, the x and y components are smaller, okay? So that's why the bottom number is a hypotenuse. Okay. Now, let's talk about the reactions. It's a fixed support, so remind me, how many reactions are there? 3. So there's a vertical reaction, which I'll assume acts upward. There is a horizontal reaction, which I'll assume acts to the right. Okay? And there is a moment reaction. Now, I will ask you, and there's, again, with assumptions, there is no right or wrong answer. Would you like me to assume clockwise or counterclockwise? Counterclockwise. Okay, so we'll assume counterclockwise. So we'll put something like that. Oh. And I'll call it MA. If you want to call it A sub M, I don't care. Whatever you want to do. Okay. Now, why am I saying that cantilevered beams are easier to analyze than simply supported beams in terms of the computation of support reactions? Okay, so let's just have a discussion about that. So here's a simply supported beam. Okay, we have the beam, and let's just put a bunch of loads on it. Let's put a load here. Let's put a load like that. Let's put a moment on it. Let's put a load like this. Let's call this support A, support B. Just thought experiment, okay? I'm asking you to determine the 3 support reactions on this problem. What's your strategy? Some moments where?
At A.
At A, okay. So let's think that through. Why are you summing moments at A?
Because there are 2 unknowns there.
Okay, so you're saying that there's an unknown here, and there's an unknown here, and there's an unknown here, and you would sum moments at A because 2 of them intersect, right? The key word that I'm using is that there is a strategy, okay? Like, again, you can sum moments right there and you will get the right answer, but why aren't we doing that with this problem? Because it's going to yield messier algebra, okay? And I'm saying that even with a simply supported structure, there is a strategy for how you sum moments. Like, let's go back to this problem. This problem was a mess, right? Again, I was imagining that a lot hadn't thought about summing moments here, but do you see that this is a strategy? Summing moments here is a strategy. Summing moments here is a strategy. Summing moments all the way up there is a strategy, okay? What I am getting at is, let's take a look at this problem. All the reactions are all at one point. There is no, well, we have to figure out where to sum moments. We have to figure out things. We can just do it right here, okay? Here's the other nice part about it, okay? Let's talk about this, okay? You said some moments, right? Okay? Let me ask a question. Is there a reason for this problem? Okay? Why don't we do this first?
Because it wouldn't give us a solution to either of the unknowns.
You're exactly right. If we did this, we would get that AY plus BY equals something. But it wouldn't isolate AY, it wouldn't isolate BY. But look right here. How many unknown horizontal reactions do we have?
1.
How many unknown vertical reactions do we have? How many unknown moment reactions do we have? So not only does the strategy part go away, but it really doesn't even matter what order we do these in. It mattered what order we did this in to make the problem easier. Oh, bless you. All that goes away with a cantilevered beam. Just do it in whatever order you want. So that's exactly what I'm going to do. I'm going to sum forces in the x direction first. No, I'm going to sum forces in the y direction first. That's something that we've never done first, but I'm going to do it first because I can. What?
Nothing.
No, share with the class. This is gonna be good.
Okay, do you want that? I can't. The spotlight on me, it won't be as fun.
That's okay. I'll let you off the hook. Okay, so, I love my job. Okay, so we have forces going up, forces going down. What do we have going up? We have
AY.
AY. What do we have going down? We have 10 kips times 4/5 and 20 kips. So that means that AY is what? 10 kips times 4/5, that's 8. 8 plus 20 is 28, so that's just 28 kips. Does that make sense? Again, all the strategy element goes away. You can do it in whatever order you want. Okay? Let's sum forces in the x direction. Okay? So what do we have? We have AX to the right. We have 10 kips times 3/5 to the left. So AX is 6. And then if we sum moments at point A, okay? So let's just be clear. We're summing moments at this location. Do we need to consider AX or AY? No. They are force reactions that are going through the point of entry. But we do have this moment reaction at A that we have to consider. And so I'm just going to lump that in as an MA. Okay? So, there we go. Okay? What other components generate moment? Okay, so let's look at this angular load. Do we have to consider the horizontal component? No, because it's just going right through A, right? But what about the vertical component? Do we have to consider that? Okay. Which side of the table, left or right?
Left.
Times a moment arm of?
10 and
Okay. And then we have the 20 kips times 20 feet, right? And so that's going to be 400. That's going to be 8 times 10, 80. So that's another thing also about cantilever beams is often when we have a simply supported beam, we get like an equation that we have to solve. We're not even really having to solve anything because it's kind of already solved for us. So we get that MA is positive 480 foot kips. So let's digest that. So that's 480 foot kips. And how do I draw the arrow? What do I do? It's a moment, right? So I draw it like a counterclockwise moment, okay? Because again, what matters is magnitude and direction. Remember from statics, moments are vectors, okay? They just rotate around the axis of equation. Remember right-hand rule? So when we're dealing with moments, if we're talking about statics, okay, the moments are about this axis, and they rotate either this way or that way, okay? So we have a counterclockwise moment in this fashion. So what do we have? We have AX is 6 kips this way. AY is 28 kips this way. MA is 480 foot kips that way. Okay. All right, does that make sense? Okay, I just want to show you something real quick on the homework. Come on. Is he going to pull up the solution? All right, so I will say that one of the problems is in metric. Oh, come on. Okay, well, it kind of froze for me. But one of the problems is in metric, but I'll say that I don't think that actually really matters for the purposes of the computation of the support reaction because, I mean, the loads are in kilonewtons per meters. This is in kilonewtons. But unfortunately, this kind of froze, so I'll just say what I was going to say. I got these problems out of a different chapter in the book, so we're on chapter 3, but these problems are out of chapter 5, okay? So because of that, so the problem in chapter 5 is asking something different. So it's labeled, for example, like point A and point B right here, but I'm interested in the reactions and there's no label. So I don't care if you call this like C and D. For the this one's a cantilever beam, so like this is point A and point B, and there's no letter for the supports. So like call it whatever you want, but just wanted to mention that the supports are not labeled because they're in a different chapter of the book, and that's not what those problems were intended for. But I want you to calculate some reactions for these problems. So sound good?
Yep.
All right, that's all I got, everybody. I will see you all on tomorrow.